Hey everyone, welcome back. Have you ever wondered how you could just bottle up the energy of something that's moving super fast, like a speeding train? Well, today we're diving into something that's just as powerful. We're talking about storing energy in pure, raw, spinning motion. And believe me, this technology might just be the secret weapon to keeping our lights on. So let's get right into it. Okay, so before we get into the cool physics, we really need to understand the massive challenge our power grid is up against, every single second of every single day. Seriously, it's this incredible high-stakes balancing act, like our entire power system is walking on a tightrope.
So that begs the question, right? What's the secret sauce? What's actually stopping a citywide blackout every time 1 million people decide to turn on their air conditioners at the exact same moment? And the answer is a perfect, instantaneous balance. The amount of electricity being generated has to exactly match the amount being used. I'm not talking approximately or on average over an hour. I mean right now, this very second. If that balance is off by even a tiny, tiny fraction, the whole system can get unstable and, well, collapse.
Now, this used to be a little easier to manage. The traditional grid, it relied on these huge, predictable power plants. Think giant spinning steam and hydro turbines just humming along, giving us a nice, stable flow of power. But the modern grid, it's a completely different animal. We're adding more and more solar and wind, which is awesome, but they're also unpredictable. The sun goes behind a cloud, the wind suddenly dies down, and bam, that perfect balance is in serious jeopardy.
So how in the world do you manage this new, more volatile grid? Well, this is where things get really, really clever. Turns out you can fight that instability with motion itself. Let's dive into the super elegant physics of kinetic storage. Kinetic energy storage is pretty much exactly what it sounds like. It's storing energy in an object that's moving. So forget about all the complicated chemistry inside a lithium-ion battery for a second. This is way more fundamental. It's basically a mechanical battery. So how does this mechanical battery actually work? Let's take the flywheel. It's really a beautiful, simple three-step dance. Step 1. You accelerate. You use any extra electricity on the grid to spin a really heavy rotor up to some mind-bogglingly high speeds. Step 2. You store. That spinning mass is now holding on to an immense amount of kinetic energy, just in its momentum. And finally, step 3. You release. The grid needs a little boost. The flywheel's momentum kicks in, drives a generator, and converts all that motion right back into electricity in a fraction of a second. It's that fast.
Now, flywheels are the real heavy hitters here. They're great for storing big chunks of energy for a few minutes at a time. But there's another key player on the team, this supercapacitor. While flywheels store energy mechanically in motion, supercapacitors do it electrostatically. Their superpower isn't about storing a ton of energy, but about being able to charge and discharge it almost instantly.
And look, this isn't just some theory stuck in a lab. Kinetic power is already out there, in the real world, making things more efficient. Let's look at a few examples, from the bus you might see on your street all the way up to the entire power grid. Okay, let's start with something we can all picture, a city trolley bus. Every single time that huge vehicle hits the brakes, it's generating this big burst of energy. And normally, that energy is just completely wasted as heat. But what if you could actually catch it? And that's exactly what supercapacitors do. They are absolutely perfect for this job. They can instantly soak up all that energy from braking, hold on to it for a few seconds, and then release it to help the bus accelerate from the very next stop. It's brilliant. This not only makes the whole system more energy efficient, but also keeps all the electrical parts from overheating. All right, let's scale things up a bit to microgrids. Now, microgrid is kind of like a small, self-contained version of the main power grid. You might find one powering a hospital, a military base, or even a remote town. And they usually use a mix of things like solar panels and backup generators. For a microgrid, stability is absolutely everything. And this is where flywheels come in to act as this crucial stability anchor. So, say a big cloud covers the sun, and the solar output just plummets. The flywheel instantly kicks in, releasing its stored energy to keep the voltage and frequency perfectly stable. It's like the ultimate power manager, boosting reliability no matter what happens.
All right, now for the big one, the entire power grid. That same idea of stability applies here, just on an absolutely massive scale. See, the frequency of the grid, you can think of it as its electrical heartbeat, has to stay incredibly steady.
So, to keep that heartbeat steady, power companies actually use huge arrays of flywheels all working together.
Get this, when demand suddenly spikes and the grid's frequency starts to drop, these flywheels can inject a massive burst of power before a big traditional power plant can even react. We're talking stabilizing the frequency in milliseconds. They provide this incredibly fast regulation, which makes the whole system more responsive and even cuts down on energy losses.
So, when you put all of these different pieces together, what's the big picture? What's the real payoff of harnessing this elegant power of motion?
You know, as our grid gets more and more complex, just making power isn't enough anymore. We have to master controlling it. And that is the absolute key takeaway here. Dynamic, split-second control is what makes a modern power system truly reliable.
And this really sums it all up beautifully. You've got supercapacitors handling those quick, small-scale jobs, like grabbing braking energy in a bus. Then you have flywheels providing that powerful stability for a local microgrid, and when you group them together in arrays, they regulate the very heartbeat of the entire grid. It's a perfect case of using the right tool for the right job at every single scale. So what's the end result of all this? We get a power grid that's just fundamentally stronger across the board. As you can see, kinetic storage really delivers on the three things we need the most: stability, reliability, and efficiency. It is the trifecta that we need to build a truly resilient power system for the future.
Kind of makes you think, doesn't it? We so often look to these super complex chemical or digital solutions for our biggest energy problems. But maybe, just maybe, one of the most elegant and powerful answers has been right here the whole time, hiding in the simple, beautiful physics of a spinning wheel. Is the future of energy already in motion?